LeetCode 339, Nested List. Weight sum isn't just a nested list puzzle. It's a glimpse into real-world data structures where depth carries meaning. Think JSON configs, analytics layers, or recursive file trees. Each level adds weight. So how do we process these efficiently without unraveling in the mess? Optimization isn't a bonus here. It's mandatory. Let's dive in. All right, ducklings, let's waddle into the brute force route. It's simple and Quack approved. We'll first gather all the integers, then separately track how deep each one sits. Not elegant, but it floats. To prep for flattening, I'll create two lists, one to stash every integer we find, and another to tag each one's depth as we go. With both containers ready, we'll traverse the entire nested list using a helper method that captures both value and depth as we descend. Once we've collected everything, we initialize a total. Then we walk through both lists together, multiplying each integer by its depth to compute the weighted sum. After that final pass through the data, we return the total we've built up. Let's unpack the recursive helper. This function processes each element in the current layer and keeps track of how deep we are as we dive. When the element is a single integer, we drop it into our list along with its current depth, locking in its weight for later. If it's another list, we dig in deeper by calling the helper again, bumping the depth as we go one level down. With brute force, we scan the entire structure and stash every value. That's big O of n time and space. For 10,000 integers, we're looking at 10,000 operations and 10,000 storage slots. Not great if your data goes deep, space can balloon fast. So how do we clean this up? Instead of collecting everything, let's walk the structure once and compute weights in real time using recursion. We'll start with a public method that kicks off a recursive depth-first search. Since depth matters, we begin our call with depth set to 1. Inside our recursive helper, we'll need a variable to keep track of the sum for the current layer. We process each item in the current list, one by one, checking what kind of value we're dealing with. If it's a flat integer, we multiply it by the current depth and add the result to our running total. That locks in its weight based on nesting. If we hit a list, we dive into it recursively, increasing the depth as we go deeper. Once we've finished all items at this depth, we hand back the accumulated sum. This recursive DFS keeps it sleek. We still have big O of n time, one full pass, but now space is big O of d, the max depth. That's stack frames instead of big lists. Unless your nesting is extreme, it's efficient and interview-friendly. So we kicked things off with brute force, storing every number and depth like hauling pebbles across the pond. Then we streamlined it with recursive DFS, computing weights as we go. Cleaner, faster, and lighter on memory. Big O of n time, minimal space, and code that scales. Exactly what top-tier interviews and real-world systems demand. Recursion doesn't just solve problems, it simplifies them. So, where else can recursion cut the clutter? Keep diving deeper, and you'll find out.